Hello everybody, welcome back to Embetronics. This is the part 5 of the STM32 Bootloader series where we will learn how to update the firmware or application over the air. I would recommend you to go through the previous 4 parts for better understanding. Before starting this tutorial, let's see what we did in our previous tutorial. Previously, the STM32 Nucleo board is connected with the desktop or laptop using the USB to serial converter. So, both are communicating through the cable. The firmware or application was sitting in the computer. The firmware or application is parsed using the PC application which has been developed previously. If we want to update the firmware, then we will press the user boot button when the bootloader starts. Now the bootloader will be waiting for the data over the UART. The PC application sends the data to the STM32 by following our protocol. Bootloader writes the received data to either slot 0 or slot 1. After that, the bootloader copies the data from the slot to the application area and boots it. This is how we are updating our firmware or application with wire. Let's consider this scenario. When you deploy your product into the field, do you like to connect the computer and STM32 board then flash the firmware every time? No, right? You may like it, but I never like this process because I don't want to touch the hardware every time. To avoid that, can we update the firmware without wire? Yes, that's why I came up with this tutorial. In this tutorial, I have connected the STM32 board and BT05 Bluetooth board. You can use any Bluetooth chip like ESP32HM module etc. which supports BLE. These BT05 pins are connected to STM32's user 2 pins. The BT05 gives you the received Bluetooth data via UART to the STM32. The mobile application is connected to the BT05 via Bluetooth. When the chip power up, the bootloader gives control to the application that blinks the LED. When the OTA is available, we don't have to press the reset button and user button. The mobile app will inform the BT05 via BLE. We have developed the Android application for this purpose. Then the Bluetooth module sends the data to the STM32 via user 2. Then the application gives the control to the bootloader so that the bootloader can start the OTA process. Then the mobile application sends the firmware package data to the STM32 board bootloader via Bluetooth. And it writes the data to slot 0 or slot 1. Then it copies the data to the application area and runs the new application. This is what we are going to do it now. It makes sense, isn't it? In this tutorial, I won't touch the bootloader, so it will remain the same as our previous tutorial 0.3 version. Now, we will add the OTA feature to the application so that it will give control to the bootloader when firmware OTA is available. I am enabling the user 2, so make the PD6 as RX and PD5 as TX. Then go to connectivity, user 2. Change the mode to asynchronous. Make sure the baud rate is 115200. Then enable the user 2 interrupt and generate the code. Here, let me include the ETX OTA update.h file so that we can use some macros that we have created already. I have added the header file to include directory. Then change the version to 4. It was 3 earlier. We will have to receive the UART data asynchronously, so I am using the interrupt method instead of polling. I have added the HAL UART receive IT function which tells to receive the 3 bytes data from the user 2. Whenever we receive 3 bytes, this HAL UART RX CPLT callback function will be called. There, we will have to check that we received data from your user too. If so, check that we have received the string OTA. The Android app will send the string OTA to STM32's application to start the OTA process. Then the application changes the reboot cause as a OTA request and writes it to the flash. After that, it resets the controller. Now, the bootloader will take care of the OTA process. If we didn't receive the string OTA, then we will again schedule the RX. Now, when the bootloader starts, it will read the reboot cause as OTA request. So, it will wait for the OTA data. Let's build the application. Now, I follow the previous tutorial steps to flash this application using the computer. See, the 0.4 application is running. Now, this app supports the OTA. Let's verify this OTA update. For your information, I have changed the BT05's baud rate to 115200 by using the AT command baud 8. The default baud rate is 9600. I will change the application and add new red LED blinking. First, I will change the application version to 0.5. Then add the new LED. The red LED is connected to the PB14. So, set that as a GPIO output. Save and generate the code. Let's blink the red LED also. Build the source code. I will copy this new application to my mobile. Now, the blinky bin is copied to the mobile storage. See, the bootloader version is 0.3 and application is 0.4. Blue LED is blinking. Now I am going to flash the 0.5 application where we blink the blue LED and red LED. We have developed a simple Android application using Flutter to demonstrate this OTA update. Open the Flashy app. Connect to BT05. There are many characteristics available. I am going to use the last custom characteristics for our communication. Select write. Then select the binary file which we want to flash. Then start the OTA process. The OTA process has been started. I have just simply learned the Flutter in a few days and wrote this app. So this Android app is a very basic app and it may have many bugs. Even if you click the cancel button, it won't react because I am running a for loop which makes the UI hang. I don't know the proper way to handle this. If you are able to fix this problem, please give us the solution. And also, we are not taking care of the response that STM32 sends for each chunk. You can add that too if you are able to fix that. This OTA process took almost 18 minutes. Yes, I agree. For just a 20 KB file, it is taking that much time. It's huge. We can optimize it. I am leaving this optimization to you. See, the new application has been flashed successfully. New app 0.5 is running now and see the LEDs. Both blue and red LEDs are blinking. That's it. I have given the link of the source codes in the description. Please check it out and support us. Thank you for watching. See you again in another good tutorial video. Take care.